All right, so pattern recognition is one of the four components of our computational thinking. The four components being pattern recognition. We had decomposition, we had abstraction, and we had algorithms. So pattern recognition is what we're going to look at in particular here. So that's represented by this diagram here, where the whole brain represents all of computational thinking. And we're focusing here on pattern recognition. One of the pillars. The other pillars are abstraction, decomposition, and algorithms. So pattern could be repeated. We see this a lot in mathematicals. So computational thinking probably includes mathematical thinking, or it's certainly really closely related to it, but it includes it. So maybe you can see patterns here. Now, generally, when we look for a pattern in a series of numbers, we try and see if there's a relationship which repeats between consecutive numbers. So, for example, is there a relationship between 2 and 6 and 6 and 10 and 10 and 14, which is consistent? What's +4? That would be the relationship, and that works. You can test it. 2 + 4 is 6, +4 is 10, +4 is 14. So basically, if you had n and n plus 1, so n plus 1 is equal to n, not +1, but +4, right? So the other one, the next one, is a relationship between the first and the second and third, which is repeated and consistent. Multiplied by 3. You guys are seeing this real quick. That's really great. That is true. 2 times 3, 6 times 3 is 18, etc. Now the next one, it's easy for me to see it because I've looked at it a lot, but it might be a little bit harder for you to see it. It's actually called a Fibonacci series. Fibonacci, or Fibonacci, probably because he's an Italian dude. Yeah, I bet it's Fibonacci. He's mathematician from more than 100 years ago, and he sort of described this series. It might be hard to see because what you have to do is you have to look at more than 2 elements at a time. So what you have to do is you have to look at these 2, and what's the relationship between those 2 and this? Add them together right now. Get it? You see? So you take the first 2, add them together, you get the third. Get the next 2, that gives you the fourth, right? Those 2 together, that gives you that. What do you think the next one will be? 13. Yep. And it continues. That's a Fibonacci series. You just take position 0 and 1, add together gives you position 2, and etc. So yeah. All right. So here's some other patterns that we've come across, and there's a little note there about that, about Jacquard. Remember that from lesson 1? Here's Jacquard's Loom. What Jacquard's Loom had was it had these instructions, which would be an algorithm. The instructions were a program, right? Like holes in the wood that lined up with little spindle things that went through. And because of that, you could get a pattern. Now, the benefit of the Jacquard's Loom was it could do things that people could do, but it could do them a lot faster and with quite a lot of precision and accuracy. So using a automated loom, you could get a pattern which was very accurately reproduced quickly. That's not always what we want in a pattern. So, I mean, we do spend very good money to have people do this by hand. And we can tell that they did it by hand because it's actually a little less precise, right? We can see some variations, and we'll pay money for that. And of course, some people make a good living out of that. I guess in places like Iran and Turkey, they do that. And probably you could think of some other places too. Afghanistan, I think they do that. All right. So here's another pattern that we see. If you're running a business, you want to keep control of your money. You want to know what happened to it, where did it go? And so whenever you sell things, you'll insist on a receipt being produced. Your company will produce a receipt. That way the accountants, etc., can go and check that the money coming in relates to the product going out. And also your customers are able to look at it and see exactly what they paid. And then they can use their receipt to input into their computer systems so that they can see that their money going out relates to their product coming in. So you wouldn't want, you could write this by, sorry about that distraction. That's just the previous recording. You could have your bookkeepers write this out on a piece of paper, but it'd probably be better if you had at least a pro forma piece of paper, or if you had a computer program to do it. So this would be very easy to sort of put into a algorithm or produce a receipt. You could use a program to do that. There's all kinds of accounting programs. You could probably even have somebody write something in Excel to do it. But the important thing is that it would be consistent. So there's a pattern there. Every time you see a receipt, you know that the total's down here. You know that you can get your unit prices here, descriptions. Okay, I'm going to move on because I can see that's boring people. Nobody's interested in business stuff, right? Pattern recognition. Two types of patterns that we might notice, patterns that happen across different the problem is similar, but the context is very different. We're going to look at that, right? So we've got an example coming about averages. So we can have very, very different contexts for the same type of problem. Or we can have a system, and inside that system, we see the same pattern repeating itself. Let's look at those quickly. So firstly, let's look at, oh, well, it's the next slide coming, I suppose. Do we automatically look for patterns? I don't know. If I'm seeing a pattern, and that is a skill, and I think it's a skill that you can develop, but basically try and look for sort of variations. If I see a variations, then I see if that variation repeats. I'm not going to say that I'm an expert in noticing patterns, but we all kind of do in a way. Anyways, so now back to the thing we were going to talk about. We got two different situations where we might notice patterns. So here we have the first example is we are going to do averages, but we're applying them in two very different contexts. One is we have an athlete which wants to know how far on average they throw something, because we measure that, and you can, you know, if you can throw it further than other people, you can win a prize. So maybe you're going to throw that thing many, many, many times, and then every time you measure it, and then you want to know what is your average, and you might want to see if you might want to get a different average every week, and so see if you're improving or changing. So that would be a use of an averaging program. And I think we all understand the concept of an average, where we add up the total of a bunch of events, and then we divide by the count. Total divided by count is average. Meteorologists could do the same. Meteorologists would say, I want to know what's the average temperature, the average for the month, the average for the year. So it could measure the temperature a lot of times. In this example, it's saying measure it every hour. Yeah, we could do that. And then you could get the average for the day, or for the week, or the month, or the year. That would be a lot of measurements, right? But the way that we would actually implement that would be the same as we did for the athlete. Take all of the measurements, count how many there are, total them up, divide by the count. That's your average. So we could write a little module which just calculated averages, and we could use it for both of those problems and many, many other problems. And in fact, people have done that. You'll find that average is built into your Excel spreadsheet, right? You don't have to write a program to do the average in Excel. It's already there because it's something that we use all the time. It's a pattern that somebody noticed, and so they put it into Excel, right? Drawing polygons could be, no, I should have a diagram for that. Yeah, let's look at that. Oh, I didn't use the second one, right? Let's look at the second one, which is, what if we had a business, and the business needs to keep a record of all the people that are sort of part of that business? So that would be the salespeople, the managers, but also our customers. So what would we do? We would probably have some way of getting from them some personal details, which would then be used for their profile. And so you could have a profile development module. All right. And even so, it's inside the business, but we got different components: managers, salespeople, customers, and we extract the same kind of information from them. Like the idea of, sorry, AP. SAP. Oh, very good. So you're talking about the large company that makes computing software, the SAP. Yeah. Yeah, they do all that kind of stuff. Yeah. Good. All right. So I'm sorry. Sometimes my hearing is not all that great. You could say that here's a problem, which is to draw a polygon having different sides, and we got different polygons. So we got polygons like a triangle all the way up to a decagon. Now they have different number of sides. The angles are part of the description of that. So for example, a triangle, all of the angles add up to 180. With a square or a rectangle, all of the angles add up to 360. And likewise, these other ones, the angles add up to different amounts. Also with, there's some features about a triangle. The length of the side is going to be proportional to the angle. So there's some sort of just mathematical features about them that you could include in a algorithm so that you could very easily sort of just say, go and draw this. So we would know to draw a triangle because we'd say, okay, draw this length there, then draw this angle, then draw another length, then another angle, and we could get back there. Likewise with, we could use the same program, I guess, to make a quadrilateral. There's the length, there's the angle, there's the length, there's the angle. With each of these, the same kind of idea, right? Length, angle, length, angle, length, angle, then fill. Now, each of these things here, we could refer to as kind of being a thing called a class. I'm not going to go into explaining to you a lot about object-oriented programming. I just want you to recognize the term because later in your studies here at the college, you'll learn a lot about object-oriented programming. Python programming language, which we're going to use in this course, is an object-oriented programming language. The idea with object-oriented programming is you have objects. Objects have attributes or classes. And you could have an object, which would be your polygon. And then your attributes would be how long is each side and what is the angle. And from that, you could produce these things. So you'll come across that. Here's an example of that also. Again, this could be done with object-oriented programming. You could make a method class that would be something to do with drawing a circle. All right, or it could be a function. And that could be used to solve this entire problem. This entire problem of drawing a happy face could be solved by drawing a bunch of circles. I hope you can see that, right? So what we could have a circle program. So here's a circle, here's a circle, here's a circle, and here's a half a circle, right? And so if we knew things like what is the diameter of that circle, what is the thickness of the line around it, where is the center of that circle? In this case, we've got an arc. So what is the arc of that circle? The arc being a number of degrees out of 360. And here it refers to it as a cut or something. Yeah, all right. But if we know those details, we can just take a circle object, or we could take a circle routine, and we could draw this diagram. And I think that's in the next slide. No. Yeah, what we need to know is we need to know the diameter, the color of the line, the fill color, the size of the cut, which I referred to as the arc. And you'd probably also want to know what's the center of the circle, coordinates of the center of the circle. Yeah, all right. So I thought we were going to have a function about that. Yeah, it's down there. It's sort of 4 slides away. We'll get to it. You'll see the function or the subroutine that does the circle. But here's another diagram where we're using a bunch of objects. You can imagine each of these being an object. So if you wanted to simplify this down, you can see that we've got some rectangles. So the house itself is a rectangle. Each of the windows except that one are rectangles. We got a triangle. We got a bunch of triangles there. I got circles. And actually, if you looked at this, you might say, oh, well, that's a more random shape. But if you looked at it carefully, you'd see that that's pretty circular, right? Basically, you could just have a bunch of circles overlaid over top of each other, and you'd end up with that. And you can see that that's a rectangle. So just using a fairly simplified approach, you could just go with some rectangles filled in with different colors, put in different positions. You know, the rectangles have got different widths and heights. There's some more rectangles. Oh, we got some lines too, or those could just be rectangles, very skinny black rectangles. We got some triangles. And if we know enough about those, we could just draw this using a computer with just some simple programs, the modules being a rectangle module, a circle module, and a triangle module, and you could build that. So that's what we got here. We got a rectangle module, and what we need to know, we'd need to know the width, the height, the border, and the fill, and we could draw all of these rectangles. Circle module, knowing the diameter, the border, and the fill, we could draw those circles. And a triangle module. And the triangle, we need to know a little bit more because we need to know the rotation of the triangle because these triangles have different orientation. This won't come up in the exam. The feature that you need to know for the exam is that we can break a problem down into small parts and we can code those small parts. I think that's going to come up in a couple of slides. The subroutine thing. So we could have a module for a circle. We could have a module for a rectangle. We could have a module for a triangle. That's the kind of thing that you need to know. And we reuse them over and over again. And we get like different circles, different triangles in the right places. Oh, what about this? All right, so there's more than one way to bake a cake, I suppose. But there are some, can you see some patterns that are the same? I mean, what I see is that, because we're talking about pattern recognition, right? Preheating the oven and baking, blending, but we got some things that are out of order. And I mean, that are in different order. The whisking could come before or after. Yeah, okay, so, but there is a pattern there. I think the idea there is, do we recognize any patterns? I guess I kind of do. We have patterns and we have slightly unique patterns as well. Okay, we try and find patterns, and if we can find a pattern, maybe we can solve a small problem. And this is what we do with 3D design in games. So, you know, with a game, what they'll do is they'll get a figure, they get a design for the figure, and then the figure moves all around the screen, right? You get a kind of movement, up, down, sideways, etc. Your game just is made up of a bunch of components like that that are sort of fitted together. And yeah, so the program starts out with a bunch of, it might seem like a very complicated program, but the individual bits are sort of broken down to something that's kind of small. This is this figure, this is this movement, up, down, sideways, down, whatever. Now I finally get to the subroutine thing after several slides in the thing. So what we actually have is we have a little program, or you could think of it as a object. Well, let's call it a program. And we have some inputs. The inputs here we could refer to, we use different words for them. Sometimes they're referred to as arguments. We also use the word parameters. So these are parameters which are going to be inputs to a function. And so depending on how they are, we'll get different circles, right? So one of those is going to be a 50-50 3-centimeter black circle, and one of them is going to be a 45-45. I'm not sure what the first thing is. Yeah, that's XY is going to be the center of the circle, I guess. So that's a coordinate. So coordinates, diameter, how wide is it? What is the border? Is it filled or is it cut? So only one of those has got a cut. It's 50% of a circle, and they all have different centers. One of them's got a different color, blue. That's, yeah, anyway, so the important thing that you should see there is it's the same little program. What the programmers would have done is they wrote this little module called draw circle, and draw circle takes these inputs, and based on those inputs, it makes these outputs, right? So one of those things gets this big circle, which, yeah, the 3-centimeter circle, one of these, and then we got these 0.5-centimeter circles, just based on the different outputs. But they're all just the one little program, which is draw a circle. And from that, we can get this bigger thing. So that's a modularization from a pattern recognition. The idea of a subroutine is very important in programming. And I hope that I can give you some example of that when we do our Python programming. So the idea is we know how to do one part of our program exactly right. We do a subroutine for it, and then we can reuse it as we need to. Reusable code, very important in modern computing. How we doing, guys? You're not falling asleep yet? Soon, though. If you don't, I will. The idea of moving backwards. A few minutes ago, we talked about we need to know what is the ideal, what is our goal. Once we know what our goal is, we want to move from where we are to there. And so maybe we can imagine what it's like to be almost there. That would be moving backwards. And then almost to almost, you know, eventually, so we can go backwards from where we want to be. That's another way of sort of doing our planning. You use that, as it says, in calculating a route or whatever. All right, we're almost done, so don't worry too much. I will try and go through this kind of quickly, I suppose. Pattern recognition is what we're doing here. This lesson was about pattern recognition. Now, we got two different things going on here. We've got this thing which is, we got facial recognition, where we're recognizing a particular individual. And we've got one which is just recognizing that there is a face. Okay, so we can recognize, we might not be recognizing who these individuals are, but we can recognize by certain things that the computer has been programmed to sort of notice that, for example, this is a face with two eyes and a mouth in a certain proportion, and that's probably a human being. So therefore, we can go and calculate that. So the same computer program could be given this picture, and if it's been developed properly, it's going to say, well, yeah, okay, that's got eyes and a nose, but it's not a human. And so with the right amount of, you can train computers to do this using artificial intelligence, right? Feed them enough pictures and they'll be able to sort of see averages. So for example, we would notice that the average distance between the eyes in these animals is different than the average distance between the eyes of humans. This is outside the normal range for humans. And likewise, the distance between the middle of the eyes and the mouth or whatever, or the way the nose is, that's different in a cat than it is in a human. So without too much trouble, you could get a computer to notice the difference between a cat and a human, even though we were looking here for eyes and nose and stuff, and eyes and nose are here. Now, the other thing is, so we've got a thing which just recognizes this is a human. And then we've got this thing which is on our phone, which recognizes not just that it's a human, but it recognizes that it's a particular human, right? So I have some security on my phone. I can use my fingerprint. I can use a special code, or I can just use my face. So the computer is able to notice not only that it is a human, but it's a particular human, this human. And so, whereas here we were looking at like the average distances between eyes and nose and things here, in this one, we would be looking at the exact proportions on a particular face, right? So on this particular face, relative to the width of the head, the eyes are exactly this far apart. The nose is exactly this percentage of that width, etc. And that will be the same, even though I get older and my skin gets a bit more saggy or whatever. That's not the things that it's going to be looking at. What it's going to be looking at is that distance between the pupils relative to that distance between the width of the head, because that your head's not going to change its shape, you know. And so just based on that shape of the head, we'll be able to know that that's you or me. So that's kind of cool. All right, so we're supposed to know what these are, I guess. I hope that I've given you this and I've covered that enough for you, that you know what decomposition is. From the diagram, you could tell me decomposition would be complex problem broken into smaller problems. Eventually, this problem is small enough that you can solve it. Then you solve those very smallest problems. Then we sort of put them together and you've solved the big problem. All right, the next one. Pattern recognition. Similar pattern, and then you solve it and reuse it, right? Solve and reuse, solve and reuse. I only have to do this once and I can use it again and again. Abstraction. looking at it from different angles. But yeah, but it's really just focusing on what's important, ignoring everything that's not important. So there's a lot of stuff that we don't really care about. So this is a cube. We only care that it's got 4 sides. So just focusing on what's important, ignoring what's not. Algorithm is your recipe to cooking something, right? That would be step by step. I like that. Step by step. All right. So here's some questions. You answer the questions and then we'll go. All right. What's computational thinking? One of the best answer, what the other two are not. Using a set of techniques, approaches to help solve. I like that. Thinking like a computer. Nope. And giving instructions. Nope. So you were right. C. I'm going with C because you went with C and you were right. Okay. This one. Why do you need to think computationally? Very good. So that means you're listening because it's something that everybody should be able to do, right? It's not just for programming. It's everybody should be able to do this to solve problems because everybody has problems. This one. Because you very carefully noticed that the word there was not, right? Not computational thinking is coding. Those other things are very good. Coding is only done by computer programmers. Computational thinking is not the same as computer programming. Which of the following is an example of thinking compute? So this one is wandering around randomly. Is that computational thinking? No, that's not. Planning. When you are doing the planning, that's computational thinking. If you just ask somebody else to plan, that's not computational thinking. So good answer. All right. So which of the following is not computational thinking? Oh, big clue in that one. Huh? They all got it.
Yeah, I was saying C.
C. I like that. Accidental. That's not computational thinking. The other one's got the clue in the first word. Planning. Planning. That. How much did that show up? When we're planning things, we're probably thinking in a computational way. Wow, there's a lot more questions. Let's get through this quickly. Which of the following is not an example? We did that again, right? Who? Not an example of computational thinking.
The first one.
The first one. That's, yeah. Sometimes we might do that, but that's not computational thinking. I don't think. Which is a complex problem? Get the best answer here, because none of these answers are terrible. I like C. That's the best answer. A and B are not terrible, but C is the best because it's both things, which is a problem that is not easy to solve or understand at first. Which computational thinking technique involves breaking a problem down? A, very good. To create a successful computer program, how many computers? 4. In our model, right? So it's a model. What's a model? A model is an abstraction. We talk about abstractions. We have abstracted the world of problem solving down to something that we can focus on. And we said it's got 4 parts. That's our model. You know, on somewhere, I don't know where, maybe in China or something like that, somebody else might have another model. It might work just as well. All right. And maybe it's got 5 things. You know what I'm saying? And so, you know, does that make theirs wrong? No, it just makes it different. Right? So with our model, there are 4. All right, at the moment, the model that we're using, which is, I guess, the wing computational thinking model. It's got 4 things. When a computer is most likely to use, when writing algorithms, what? Computer. Do you need a computer to do algorithms? You can do that with a piece of paper. You keep saying B and you think I'm not listening, but I am. Yeah, I like B. Very good. The computer, we use it for coding, and we're finished. Unless you have some questions. Thanks, guys. I'm sorry I look.